Okay, so welcome everyone. My name is Andreas Groll. I'm a professor for statistical methods for big data at the Technical University of Dortmund. And together with Christoph Lai, who is professor in Luxembourg, we have started this S-training events, which deal particularly with sports analytics and also injury prevention a couple of years ago. And it's very nice that we have today a satellite event from Bilbao, and we are very happy that you are all here. There's some people following us on Zoom. The classical S-training group probably will be there. And so after a long time, it's a pleasure that Christoph gives another talk himself. And so this talk will be about statistically enhanced learning, new opportunities for sports analytics and medicine. And Christoph, the floor is yours.
Well, thank you very much, Andreas. And of course, thank you very much, Dejin, for this very nice invitation and setting everything here up. It's a pleasure to be here in Bilbao and to get to know a bit about the culture of this club that I find really wonderful to discover. Thirdly, as part of the S-training, this is also a talk that I will give for our S-training group. And this is a joint work with my PhD student, Florian, with Andreas, that you have just seen in action, and with Stefan Bolas from the University of Luxembourg. And I just want to briefly mention, so the slides that you see here, these are slides that are made. So the team that I'm leading in Luxembourg, of which my PhD student Sophia is also a representative here, is we call it Team MEDAS, which stands for Modeling, Interdisciplinarity, Data Science, Applied Mathematics, and Statistics. And so this is the first time that one of Florian has created these slides with our logo. So it's the first time that I give a talk on these special slides. So So the plan is, I will start, in order to give you an idea, I will start with a case study, so which was predicting the World Cup, the male World Cup 2018. This will put you in the right framework for everything that's about to come. Then, on this basis, I will explain what we mean by statistically enhanced learning. Afterwards, I will explain how SEL, which is our abbreviation for statistically enhanced learning, allows to get better predictions. And here, I actually will come back on this case study to explain how SEL was used in it. And then I will make a brief switch to handball. I also will show how SEL can be used in handball. And finally, I give an outlook on sports medicine, one of the topics that we have already discussed before, how this might be useful in sports medicine. Okay, so let's start with the prediction of the World Cup 2018. So our goal was to make a very nice prediction of the individual matches and also get the best possible overall prediction of who could win the World Cup after all. And of course, we had a very tough competitor. You might remember Paul the Octopus, who was extremely good in getting predictions. So he was like the golden standard that you try to beat when you do something database. And so what we did was we made a combination of statistics and machine learning approaches in our modeling. And how did we do this? Well, basically, besides taking logical, I would call it, classical covariates, we also built new covariates. And these new covariates, they were built based on statistics. And so all these covariates afterwards were fed into the machine learning model. And that's then our combination of statistics and machine learning. So basically, statistics were used at the level of feature engineering to produce some very peculiar features. And of course, well, our goal was, on the one hand side, we wanted to predict the outcome of every individual match. And in order to do so, which machine learning model did we use? Well, we used a random forest. And we statistically enhanced it by means of the features that I will explain you later on. And we trained it on 4 previous World Cups. Then what we did, so besides our goal to predict individual matches at the moment when they're happening, we also wanted, before the start of the World Cup, to make a prediction of how the World Cup might end really at the beginning of the start. So we simulated the tournament 100,000 times in order to get the individual winning predictions. Overall, as we will see, the predictions turned out quite nicely. There was just one mistake in the sense of these predictions, which was that when we have run our 100,000 simulations, the country that came out as favorites was, well, 13%, so it's not very high, but still was Spain. And I guess You all remember how unfortunate this was, the World Cup 2018. It was really the day, 2 days before the start of the World Cup, that the coach got thrown out of the team. And that is, of course, something that is impossible to really model that. You never know what that implies. When a coach gets out, the team can be fired. They can say, okay, now we really want to show what we're able to do. On the other side, the training changes. So there was a huge novel uncertainty that, of course, had an impact on it. And so this is the paper with Andreas Günther Schauberger and my former PhD student Hans van Eetvelde, in which we showed the methodology. So just a question to know a bit the audience. Who has no idea about random forests? Okay, that's good. Because I wanted to give this really a very brief reminder of the random forest as machine learning approach. So it has been popularized by Leo Braman in 2001. And the principle of a random forest is, well, a forest consists of several trees. So basically, you take individual decision trees. A decision tree can be a set of decisions that you take, and then in the end, you reach to a certain conclusion. When it's a classification tree, it will be a yes-no classification that you obtain at the end of your tree based on the different features that you have. And when it's a regression tree, well, basically it is like linear regression. When you get a number in the end, just that, yeah, it's a very different way of how you get to that decision. It's more data-driven than a linear regression in which you impose that there is a linear relationship. In a single tree, you do not impose any structure. The tree basically builds itself. And so you can use this. The decision trees, you can use it both for classification or for regression. And in the end, what you do is, so from each tree in your forest, you are getting a single prediction, which is either a yes, no, or it is a number. And then in the end, what you do, when you look at the outcome of the entire forest, is that when it's a classification, you do a majority vote. Are there more yeses or more nos? And when it's a regression model, you may just average what the individual trees give you as a number. So that's the outcome of your forest. Now, how does a single tree work? Well, a single tree basically runs through your feature space, through the space of your different covariates, your different predictors. And it does this recursively. And it basically splits, so it searches for the covariate that provides you at each step the most information about what you want to predict. And it then says, okay, for this covariate, I find this threshold. If a value is higher than this threshold, then I make this split in my tree. I go to that side, or I go to the other side. And you do this recursively. So the tree builds itself like this until a certain stopping criterion is reached. And usually you search for the split that leads to the strongest difference between the two partitions that you have built in your tree. And when I say strongest, of course, this needs to be some criterion that you're interested in. For instance, when it's a yes-no classification, you might be interested in the biggest difference in, on one hand side, you have so much more yeses, and on the other hand side, you have so much more no's. Make it very simple. Now, of course, once you've done such a split, you want in each part of your tree that the observations are as similar as possible, and you actually continue doing the splitting until you reach a point where your algorithm tells you, oh no, in these new partitions that you have, which are called leaves in the tree terminology, in these leaves, when you have the data are similar enough, we can stop. So that's the stopping criteria. And this last line is, when you've never heard about it, it's not bad. It's just like in reality, when you have a well-grown tree outside in nature, at some point, it's important to cut it back such that it can grow again. And this is called pruning, and the same terminology, tree pruning, is being used here. So basically, the idea is when you do such a categorization, you might end up with tons of individual categories and really just a very few observations within each category. And that might not be nice. It might actually lead to overfitting. So you might try to do too well, in a sense, to overfit the data that you have. And so, well, you do the same as in nature. You prune back, which means you are at the end of your tree, and then you try to cut off some of the categories that do not really add that much information. That's basically the idea. And then you reach your final tree. Okay, so that's how one tree works. And then for the forest, you do this, of course, repeatedly. You grow several regression or classification trees. And the overall goal, of course, is that your trees are not all the same, because then what good would it be? If I build one tree here, then I build another tree here, and the two trees, if they do more or less the same, if my algorithm says here, okay, I make a split like this, like this, like this on that side, and for the second tree, I'm doing exactly the same pattern with the same covariates, the same splits, isn't very useful. So you must ensure somehow that your trees are different to get the most information out of it. And this means decreasing the correlation between the single trees. And this is obtained through two randomization steps. And that's why this is called a random forest, because the forest is built really at the trees are built at random. Randomization step number one is that, so you build the first tree. Let's say you build this first tree on your original data. Fine. Then for the second tree, you will not build it also on all the data, but instead you will build it on a bootstrapped version of your original data. What is a bootstrap version? Basically, this is the shuffle of your original data in the sense that here is the original data set. Let's say I have 10 observations, and I want to do a second bag of 10 observations. So I grab in my first 10, I take at random one of the observations, I put it in the second bag. Then I do the same again. I again look among the 10 observations that I had, I pull one out at random, I put it in the second bag. And it can be that some observations are taken twice or three times. So you will get a new bag of observations, which all stem from the first, but they are chosen at random, so you can have repetitive observations. That is the idea of such a bootstrap sampling. So you do this for every tree, such that in the end you end up with trees that are all built more or less on different observations. So already this is clearly making a difference between the trees, but then there is one more step, which is step number 2. Namely, it might still be that one of your predictors is extremely dominant, is extremely strong, and whatever the observations are, it might always be that this predictor is the one that the algorithm says, oh, this predictor gives the most information, so it ends up on top of my tree. But I don't want that. I don't want to have always the same covariate doing the first split. So what you do is the randomization step number 2 is at each split that you do not consider all the possible covariates, but again a random subselection of all the covariates. This implies that if there is one dominant, he will only be chosen with a certain chance each time that you start a new tree, and so you will get very different trees. So that's the basic idea. And so by having trees that are different and combining many trees, you will end up with a prediction that is much better than a single tree. It will have a low prediction bias and also a reduced variance. Now in football, what might this be? What would you like to predict? Well, you would like to predict the number of goals that a team is going to score. So that is your goal. Have a random forest tell you this is the average number of goals that one team, let's say Athletic Bilbao, might score against another team among the people that we have here, let's say against Borussia Dortmund. So what you do is, well, you define in the beginning how many trees you want to build in your algorithm. So for instance, you can take 5,000. And then whenever you get a new observation, well, you have the covariates from the teams that are playing, that you drop them down each tree in your forest, each of your 5,000 trees. So each forest will give you a number, you average them, and then the random forest outputs the expected number of goals that this team is going to score against that team. And then from there on, well, you can see what you will do with this number. Either you take this number as your prediction, let's say if it's 3.1 goals, of course, you know that you're not going to say this team is going to score 3.1 goals, but what you then can do is you can use this predicted value, for instance, in combination with a Poisson distribution. The Poisson distribution, which is a statistical model that can model the number of times that something occurs over a fixed period of time. This is exactly what you have in football, the number of goals that might occur over a fixed period of time. And so you might use this as an input for that distribution. And then with this distribution, calculate the probability. What is the probability for 0, 1, 3, 4, 5, 6, 7, or even 9 goals, as Portugal was scoring last time, 9-0 against my home country, Luxembourg. It can happen. And yeah, I refer you to this paper by Gunther and Andreas if you want to know more about how random forest can be used within football predictions. So now, for our prediction that we made for our case study, our databases were the World Cup 2002, 6, 10, and 14. And we had the following predictors. We looked at some economic factors. So we looked at the GDP per capita of a country, as well as the population size. We had some sportive factors. We were looking at winning probabilities that a certain German bookmaker Oddshead had given. We were looking at the FIFA rank of each country. So what was at that time still the FIFA had, 2018 was the time of change. They were using still their old FIFA ranking, and at that time they were switching it for an ELO ranking. So basically those two are rankings that give a ranking to a national country based on the previous games it has played. The better your ranking, the stronger you are. This is why this is a logical covariate to describe a team strength. And this is actually the particular feature that we added, which is really the statistically enhanced feature. This is the team abilities. I will not comment much further on this now, because I will come back on this later, but you can keep this in mind. This is what made the model mainly special. We also look at home advantage. Well, which team is the host of the World Cup? Because we know that home advantage does play a role. Is a team from the same continent as the host? And what is the continent of the teams? Because traditionally, it used to be that usually it was always a team from South America winning when it took place in South America, from Europe when it took place in Europe. Over the past times, this has changed, but that's how it used to be. So this is why we took this into account. Factors describing a team structure. So we were looking, for instance, at the average age of players. We were looking at the number of legionnaires, as it is called, the number of players that play abroad, do not play in the same country. We also look at the maximum number of teammates. So how many people are playing in the same club? Because when they play together in the club, well, they know how to play together, and so that should be advantages also for the national team. So this is the type of predictors we look at there. And then also we were looking at factors describing a team's coach. It's the coach's age, nationality, is it the same nationality as of the team or not? And also the tenure, how long is he playing? And all these variables, since we have two teams, we have variables from both teams when they face each other. They are incorporated as differences. And I'm going to show you this on this example from the World Cup 2002. These were the group phase in the group of France. Well, France was playing against Uruguay, and Uruguay was playing against Denmark. So these are the features that you get. For instance, for France, so here you have the average age of all the teams. These were the FIFA ranks. Well, at that time, France was number 1 because they have been champion in '98. They have won the Euro in the year 2000, so they were really strong. Nobody was expecting that they would go out in the first round. And so here you also had the odds. And this is what our model then got to see. So for the age, when we wanted to predict France against Uruguay, for France, this would be the value +3, in the ranking -23, since we always look at differences. While for Uruguay, it would be the opposite, -3 and +20. And so the model would predict for France and for Uruguay separately. But of course, since we are looking at the differences, the correlation in these predictions is well present. And so I'm showing you now here, this is what we got at the beginning of the World Cup. So we were looking at, these were the most probable group standings that our model trained 100,000 times, simulated 100,000 times, gave us. The probabilities that you see is, so these are, for each group, these were the most likely outcomes. And you can see with what probability. So in this group of Spain and Portugal, 27.7% of the cases said that this would be the final ending. So in this group, the model was, for instance, more confident than in this last group, where the model really had trouble to figure out which one would be the most obvious outcome. So that was a more equilibrated group. And now what we could see from these predictions, now I don't know how far you remember 2018, 14 of the 16 predicted clubs indeed went to the next round. So we were very happy about that. The errors that we made were, one was Poland, and the other one was, of course, the big upset in 2018, the world champion Germany, who went out in the first round. I'm showing you here some other performance, some more data-driven performance measures. So which models did we consider here? We considered bookmakers models. We considered a ranking model. I'm not explaining this in detail. That's a purely statistical model. Then we have here a classical random forest that we have fed with our features, except for these statistically enhanced abilities features. And this is then with the ability features. And we did the same with the lasso. So basically lasso means we did a Poisson regression model on which we put on top a lasso model. It's not important to know exactly what this is. The important is that we ran it once without the abilities and once with the abilities. And now here there are three different ways how we check the quality of our predictions. And these are based on all the individual matches. So here we evaluate all the individual matches from the World Cup and we average the results. So for instance, the likelihood, this is the probability for so you look for each match, you look at what was the outcome, win, draw, or loss. And then we look at, okay, what was the probability that each model said for the given outcome. And so, of course, so what we could see from here is that the statistically enhanced random forest came out as the best. And also in this category, as in the other categories, every time beating the bookmakers. Classification rate is, did you classify correctly whether the outcome of a match? So in football, typically you are bound to be at 60-something%. It's very rare to go beyond that, because you have to, of course, imagine. I think you have this in mind, but to most people this is surprising because you're like, random guessing is 50%. No, in football, of course, random guessing is 33.3%, since you have three different outcomes that you can get. So that's why in football it's very hard to go beyond these percentages. While in sports like tennis, you can reach 75% or so more easily. So this is a value that you want to get as high as possible, and the RPS is the rank probability score. This is a value that you want to have as low as possible. It's also about the predictions that you give, and so also there, the new model outperformed all the other models. And we can also see, even within the lasso, we also see that each time there is a clear improvement when it comes to when the statistical enhancement is being added. Another performance measure, well, this one here, we wanted to predict the number of goals that each team would score, and we also wanted to predict the goal difference at the end of a game. And so what you see here is the mean squared error. So this is an error. How far away were we from the true goals and from the goal difference? So these values, you want them to be as small as possible. And again, the two best models were those that were statistically enhanced. We then also took part, we learned about this international prediction competition one day before the World Cup. And so we took part in it last minute, and we played under the name of Andreas because you had to use a Facebook account, and we did not want to create extra a Facebook account for this. So after the semifinals, our model was first, and then Esportes and Números, they just for the game of the third place, and for the final they took over.
Probably it's not a human player also, if you look at it.
Yeah. That was also like several others, there were also AIs that were playing. And then we also wanted to check how good does the model do compared to humans. And so we played here in a forecast competition called Kick-Tip. This was based in Dortmund, where you can see here somebody called Borussen-Engel, which means angel of Borussia.
My secretary, actually.
And
good name, but bad performance.
And so here we could clearly see that the stats model was definitely outperforming human predictors. So we were overall very happy with what we could see. Now, as I told you, this was really achieved through what we call statistically enhanced learning. Now, time to say what is, in general, statistically enhanced learning before coming back to the example. But first, I like this Venn diagram about artificial intelligence, which we took from Goodfellow, Benjo, and Courville. Gives you some ideas. So AI spans everything. This is general learning. Robots is included there. Within AI, you have really what you call learning, and this learning is not just machine learning, it's also some statistical learning, such as linear regression, which you might want to rather put out of machine learning if you have machine learning in mind as something very complicated, purely data-driven and not modeling-driven. Then, of course, you have machine learning, where you have random forest, XGBoost, support vector machines, and so on. And within machine learning inside, you have the so-called deep learning, which are neural networks mainly. So this is a diagram of what learning is. And now, as I said, statistically enhanced learning plays very much at the level of feature engineering. We are creating new features. And feature engineering is, in general, a crucial step to prepare your data prior to your analysis. However, it is, in a sense, an underrated important step. Modeling is way more considered. And so this is, for instance, as Zeng and Kasari wrote in their paper, yet this topic, so feature engineering, is rarely examined on its own. And what we did is we actually went on Stack Overflow. Stack Overflow is a blog where several questions about statistics, data science are being asked online. And so we accessed this in June, and we saw the following. Machine learning had 831,000 views for 94 answers on questions, while data preparation just had 14,091 views. So it's nearly 57 times more views, the modeling part, than the data preparation part, which shows this imbalance between the importance that you give for, on the one hand side, data preparation, and on the other hand side, the modeling. And this is a pity, because feature extraction is important. And some features, you might want to bring this into the game, but you just don't know how, because they're not available or they're not directly measurable. In sports, for instance, the stress of a player, it's super hard to bring this into account. Yet we know that the mentality, the psychology plays a very big role. You can see this when there's a winning streak, or there's also the hot in basketball, as they call it, the hot hand principle, which you might call hot shoe principle in soccer. When you're on a streak, you just score goal after goal after goal. And I don't know if anybody of you is following the German Bundesliga. I know that some are, of course. There is a guy called Girassi who plays for VfB Stuttgart. He has now scored 10 goals in 5 games, which is something that I could never imagine that he would be doing. Last season, in 22 games, he scored 11 goals. So you can already see that this is sometimes when you're just in the flow, things just go your way. And so that's something that you might want to take into account. But how? If we move away from sports and economics, the income, you would like to measure the income of people, but that can sometimes be data that you are not allowed to have access to. So how can you then bring this into account when you want to make a study and you're not allowed, for data privacy reasons, to know all of this, or to measure the willingness to pay of people? That's not obvious. So you might want to add this information to your model, and that's in general what scientists want to do. They want to improve their model by adding information to the model. And possible ways to get some information about these tools is what you call a proxy. So this is a variable that is not exactly like stress. You cannot measure stress, but a proxy variable would be a variable that somehow can resemble the stress that a player has. And you might want to find such a proxy to add it to your model. You can also do some data transformation that allows, if you have overwhelming data that you cannot all put into your model, you can do some data transformation to, in the end, get to a quantity that you might add to your model. And statistically enhanced learning basically formalizes these data preparation steps. So get access to something that you do not have immediately measurable as a core variable. So I want to explain it on the basis of this somehow Granger causality graphic here. So in classical learning, classical machine learning, we would be here. Y is what we want to predict, and X are X are our covariates that we have, that we can measure, and we use X to predict Y. This is what you usually do in machine learning. Now, there are three different ways how statistically enhanced learning can come in handy. One is as a proxy. So suppose that we are in a situation where, well, X are our classical covariates that we can measure directly, but then we know that there is some other information that has an impact, that's stress, for instance, on the outcome Y, but we don't know how to, we cannot measure this. But we have some idea about a proxy, about another quantity that resembles W very much. So we're going to measure this quantity and add it to our predictors in order to get some idea of Y. This is the idea of SEL as a proxy. Now, it might be, this is the second situation here, it's exactly the same, but it might be that the proxy that we measure just is too big data information. You cannot put all of this into your predictor because it's just too big. In that case, what you will do is you will create from this proxy, you are going to use descriptive statistics in order to extract the most useful information from this proxy and call it here XS, and then you will add this XS to the model as your predictor. So it will be X plus this XS. And then the third situation is even more complicated. This is when you know again that there is some information W. There's some W that will have some impact on Y, but you don't even have a proxy. You do not have anything concretely measurable. In that case, and this is actually what we did in the World Cup with these abilities. Now I can say what it is. Abilities, we call this the current strength of a team. So we wanted to, for each national team, we wanted to have a way to measure the current playing strength that the team has. And for this, well, of course, you have all its previous match results, but how are you going to use previous match results as input in the model? It's not clear. So this is the last part of SEL, which is really you use statistical modeling. So we use a statistical model on all these previous matches. And with this statistical modeling, we were creating a new parameter, which we called the strength of the team. We estimated that strength. And then this new estimated quantity became our XS here. Now with some text to illustrate what I just said. The first one, the proxies. The example that I want to give you is, for instance, if you want to add in some prediction model about households, if you want to add the non-measurable concept of standard of living. What is the standard of living of a given household? Standard of living is an abstract concept. You cannot measure it directly. So what you might use is you could use the household consumption, which is something that you can measure, and use this as a proxy. That's the first situation. That's the easiest when you have something that is directly measurable. Next example, let's take it from sports. So you have two teams that play against each other, and you want to bring somehow the experience of the teams into account, or also their level of fitness. So one way that you could do this to bring this all together is the age of players. As you've seen, we have used the age. But if you have two teams of 30 players, you're not going to use all the individual ages of the players. That is just overwhelming. It's too much. And how would you enter this into a model? You have all the different ages. You cannot enter this into a model. So that's the situation when you will use a very simple statistic based on these 30 ages. Here, for instance, we use the average age, but you can also use the median age or whatever descriptive statistic that looks meaningful to you. You might use it and then have this average age as a predictor. And third level, I'm giving you this example here from wind energy production forecasting. So if you're interested to forecast the wind energy production, well, you can improve this by adding some. You might want to know, okay, how was the weather? How was the wind over the past days? So you have information of all the past days, but you're missing the essential. How are you going to add this? So what you can do then is you can use something that is like an exponentially weighted moving average of wind speed measurements over the past 7 or up to 28 days. So you get a picture, statistically estimated picture of what the the wind speed was over the past days, and then you can use this as input into your model. This is the more advanced SEL3 type of modeling. And so another diagram, if you have here, SEL is at the center of learning, statistics, and data processing. And these individual intersections, so intersection between learning and statistics, of course, is statistical learning. Between data processing and statistics, this is what you might call data mining. And between learning and data processing, this is feature engineering. And SEL is really the type of feature engineering that is at the intersection of all these. And of course, just to say a word, of course, some of these things are already being used in various models. I'm not claiming that nobody has ever before used something like a proxy or used something like an average of ages of something. Definitely not. What is the third step is something that this third SEL step is something that we very rarely occurred, but these two we have seen it. But what SEL does, it brings everything into a formalization framework, plus it adds this new level of advanced modeling features. So now if I come back to the case study I showed you before, if we look at these covariates, so this is a classical covariate. However, GDP per capita, you can consider this as a proxy for the richness of a country. The average age, I already said, is SEL level 2, but it's really the abilities that is the main novel thing that we added here to the prediction. And as a brief explanation, so how can you measure it? How can you add this information? Well, this is one way how we did it. Of course, there are several different ways how you could do it. What we did is we were looking at 8 years of matches of national teams preceding the start of the tournament. We look at all their results, and what we did is we built a probability model that actually does contain a certain parameter, which I'm calling AL, which reflects the current ability of my team L. And to do this, we were using a bivariate Poisson distribution. So bivariate Poisson is you have one team that has a certain Poisson distribution for its number of goals, a second team that has a certain distribution for predicting the number of goals, and we were estimating actually the parameters in this model on the basis of 8 years of matches. Of course, when you do this for national teams, you have to estimate the strength parameters for all the teams, also those that are not taking part in the World Cup. That's quite logical because they are part of the data set that you are dealing with. What we also used was this time effect. So basically I'm not entering detail, but what this indicates is the idea that a game played yesterday should have more impact than a game played 1 year ago or 2 years ago. So we had some time decaying factor that we added to give different weights to the different games. And here, this is the classical Poisson parameter, and within this Poisson parameter, we added the ability factors as a difference. So when team I plays against team J, it's the difference of their abilities, of their strength, that will impact on the parameter of the Poisson distribution. That's how we were estimating it. We also added a home effect parameter and some general baseline parameter. This is what I said, that we were using 8 years of matches. And now I'm showing you, so this is how we calculate the abilities. Now I'm showing you here the variable importance for the model that we used for the World Cup 2018. What is this variable importance? So basically, we were looking at our training data from 2002 to 2014. And for these 4 preceding World Cups, we were measuring how important each variable is in the prediction. How can you do this? Well, it's not complicated. You make a prediction with all your variables. Then you see how good this is. And then what you do is each time basically you take out, not exactly that, but you have to imagine it like this. You take out one predictor, and then you make again the prediction, and then you look at how much worse is your prediction. And then you can see, of course, if for one predictor, after you've taken it out, the predictions are much worse than for another predictor, well, then this first predictor has more impact on what you did. And what we could see here is that abilities by far were the most impactful one. They were the ones that were mainly driving our predictions, followed by the rankings of the team. That makes sense. You also have the age appearing here. Quite interestingly, the population goes in the other sense. So this would indicate that the size of the population should not be used as a predictor. And I think we all know some examples, like Iceland, for instance, or Belgium, which are rather small countries, but they played extremely well. You have big countries like China, for instance. China played in the 2002 World Cup, but they played very badly. So, or you also have other big countries. Canada also is not strong in football, just because in these countries it's not the main focus. So population might not be the best indicator, although of course you have countries again like Luxembourg, small country, not very strong at football. And so in this paper here on which this talk is based, is that where we present the overall idea of SEL and explain how it merges with what exists in the learning literature. And now what I will do next is I will show you some results from the handball paper that I did with Florian, which we call Supporting Sports Coaches with Statistically Enhanced Learning Predictions and Application to Handball, in which we explain how sport coaches could use these predictions. So the goal here was the same as before: predict either which team is going to win, then it's a classification model, or predict the number of goals scored by each team, then it is a regression problem. Very similar to football, where you can do the same. What are the data? So we were looking at female handball teams from European clubs since between 2019 and 2023. So we used so many games for the training and these for the test set. What were the features that we were using? Classical features that are like which day of the week were the games played. It's not national teams, so it's club teams. So that's why we use this. The hour is also important. Is an imported game. How many days remain up till the final if it was an event like a competition, or if it was a round robin tournament. Then for the team structure, here we were looking at the height and weight of players. Because in handball, when they really play position against position, that does have quite some effect in general. That's why we added it. The age, travel distance from one place to the other. Are they how many international, national, how many players play for the national teams, and so on. And what we added here, that's what I wanted to do. And the attack strength and defense strength of a team is, well, you can guess this now. These are the statistical enhancement factors that we added, and we estimated this by means of the so-called Cornwell-Maxwell-Poisson distribution. For the sake of time, I did not prepare this in detail, but it's a bit similar to what we did in football. We were looking at previous games and estimating the attacking and defensive strength of the individual teams. So now I'm just going to show you here the results that we got. What we did is we used here I'm showing you 4 different machine learning models that we have run: a random forest, XGBoost, CatBoost, and also neural net. And once we ran it with the classical features, and which are basically which are these features here, first 2 categories, and then classical plus SEL. This is where we added the new features on attack strength and defense strength. We have three different measurements of performance, but let's just look first at accuracy. What we can see is in each case, there's a very strong increase in the accuracy of the different models. For instance, here for the random forest, it's an increase by more than 21% that we gained. CatBoost also, it's 21%, 16%, 14%. So everywhere, even the neural net that already is using a lot of data and is a very complex model, could be strongly improved by these new features. For the F1 score, it's the same. It always went up very clearly. And for the Brio score is again a score that you want to have as low as possible. it's the same picture. So there was always, in these classification models, there was a very clear improvement. So this was the classification to predict the outcome of the match. As I said, we did both. We also predicted the number of goals. And so this is what we got here. Same principle. We use the same models, once in their classical version, once classical plus the new features. And well, here we have the root mean squared error, which you want to be as low as possible. And again, we see a clear, except for the neural net here, that's the only place where we don't see a change. Here, just a small change, but for the rest, it's always a clear improvement. And what I want to show here is these are the predictions that we did for the home team, and these are the predictions that we did for the away team, for the number of goals that they will score. Now, before, for the classification, it was just the outcome of the match, no need to separate. But here, of course, we were predicting the home and the away teams in terms of the number of goals. So the SEL features, they definitely add a lot in these prediction models. And again, we were looking at the feature importance, and we could see here that attack strength and defense strength, they are the main drivers for the outcomes of the matches. But that shows that that says something in general about the importance of these predictors. But what we also wanted to do is we wanted to somehow find a tool that could be attractive and informative for coaches, because this is, I mean, it's nice to be able to say, okay, listen, this is the most likely outcome of the game, and those variables are likely to be of much interest, but we wanted to try to do something more. So we tried to actually give something like this. This was a particular game that was played by the handball club of Metz against Chambray on May 17th of this year. And the prediction was 32 goals for Metz handball. And so what we can see here is how much each of the predictors actually is adding in terms of goals. So we can see here that that without the attack strength, it might go down to this number of goals. If we take the average of the wing players, for instance, this has this impact. And if the defense strength of the away team, if that were not there, then so many more goals might be scored. And we discussed this also with the coach of the team. So with that coach, we are now in exchange in order to further improve this and really look at the needs that a coach might have in order to learn. Okay, so basically we can see here, it's very important, this wing player in this particular match, it's going to be these and these players that will play the main role. So here I'm just showing you a rough overview, but what we do with the club is that we can tell them, okay, listen, in this game, these players are likely to be the most important players, or from the opposite team, the players that you should watch at, because there might be there might be a mismatch on this position or mismatch on that position. And this is what we try what we really now want to fine-tune. That's the first try, and we are on our way to fine-tune this in collaboration with the coaches. And finally, as we've spoken a lot on sports medicine, I also want to give an outlook of how this could be used in sports medicine. I say could because it's nothing that has been done so far. In sports medicine, what you want to do, you want to estimate the chance or the bad luck of an athlete to suffer from a certain injury. And as we heard before, there's already a difficulty to define what is an injury and how to classify it, but that's for another problem. So there are several challenges. The challenge is, if you want to do this in general, it's super hard because there's a big difference between sports. There's a big difference between men and women and between professional and recreational athletes. So these are already very challenging depending on the data that you have. Then sports data, they happen to be either information is lacking because it's not been written up, or they are massive. And they're also very noisy. They are incomplete. they are also not structured. I mean, those that work for the clubs, they I think know this much better than me. And they come from different sources. You might have video data, you might have image data, you might have written down data, some time series data. So there's a bit of disparity in the data that you have. Injury risk, moreover, is multi-causal because it can be due to overtraining. It can be due to a direct contact that you have during the game. This is hardly predictable when this happens. So this can be internal, as I said, or external reasons for suffering an injury. And then, of course, also very important is that the end users, which are the people who do the sports or in the clubs, they need to be able to have data-driven solutions that are user-friendly. Because if you just come with a complicated model that you show, okay, the model tells you this and this and this, but the model is unreadable, the model is not understandable, it will be of no use. So that's sometimes the disparity that you have between academia and between the real world, let's call it. So it needs to be user-friendly. So our idea with SEL here would be that we would like to add information that you cannot measure directly, such as, for instance, we would like to use SEL to model the intensity of exposure that certain athletes have to some tasks. For instance, look at how long have they trained. Find a statistical model to model the length of the training, the intensity of the training, and then use this as an input in the prediction models. Or various biomechanical tests that they do. You get the individual results, yes, but how can you add this into the model? If you can find a way to extract the essential information, that would be very nice. And then also, how can we bring domain knowledge into the game, such as medical notes, clinical guidelines, ontologies, or image data? This is very hard to interpret, but these could be super useful if we found a nice way to build this, to find a model that can bring this to a machine learning prediction model in the end. So that's the idea, that what we want to do with SEL in order to find hopefully informative covariates. And then of course, in the end, when you run such a machine learning model, when you have to use interpretable machine learning, such as what I showed you a bit before, to open a black box. You cannot run the machine learning model and just say, this is my prediction, but we cannot really interpret it because it's a black box model. No, it has to be done by means of interpretable machine learning models that allow you to explain really, this is the outcome of our model. That's the reason why we got to this outcome. And by that, I will finish, and thank you very much for your attention.
Thank you very much for, I think, a very clear and very exciting talk. Are there questions, comments?
One question around in your World Cup predictions, why did you choose in the end to use both of the ratings?
Yeah, that's a very good question. We also did it with just one of the ratings. At that time, we did it in that paper because they were there at the time. So the information was available, but for everything that followed up, we throw away, of course, the old FIFA rating, because yeah, I mean, you know, the ELO rating is built in a better way than the old rating, which had several flaws. But another reason was that for all the previous World Cups that we used in our training base, yeah, there really the FIFA ranking had a strong meaning because it was used for the seeding. So we believe for this 2018 World Cup, we should keep it in. But yeah, for now it's out. Yeah,
it's a good point, because like if you have like FIFA ranking, ELO rating, Christoph's historic match abilities, bookmakers odds, and at some point for the female World Cup, I think one time we also used these plus-minus player ratings from a different researcher from Norway. Then we had 5 variables that in all of them in some sense tell you how good is the team, right? The bookmakers odds are kind of their estimate, and the ranking is based on historic games and so on. But multicollinearity then of course becomes a problem because they are highly correlated, these variables. So if you throw them all jointly in a model, then you have to be aware of potential multicollinearity issues. And so the lasso, which puts a penalty on each beta coefficient of each variable, like on the effect of each variable, is one moderate way to deal with it. And for the random forest, the multicollinearity issue, as far as I understand, is not that much of a problem. But you have to, when you interpret the models, you have to be aware of what they do. And in principle, I think if you have already some gut feelings that, like, for example, the ELO rating, which is nowadays almost the same as the FIFA rating, but at the time the FIFA rating was too simple, then just go directly for the ELO rating, of course. Like, as long as you believe that one other variable brings in some different amount of information, then maybe put both. But it's something that you need to discuss and decide at the end.
So maybe the Olympic Games, the number of medals are easier to predict because there are many variables and many aspects.
Yes, it's definitely something where we also want to go. It's always a bit of a matter of time, and of course also taste of the people that you have in your team. For instance, why are we working on handball? Well, because Florian is a former handball player, so that always depends a bit on that and time issues. Yeah, but of course, Olympic Games is definitely also would be a goal. Yeah.
Because of the rules of the games between handball and football, for example, is it, in your experience, is it easier to predict a handball championship or something rather than a football? And also another question, did you try with another sport? I don't know, you mentioned tennis, I don't know, basketball or...
Yes, so for your first question, handball indeed is easier to predict than football, just because in handball you have more events, more goals that are being scored. Football is so difficult because, I mean, in a sense, when you just think about it, I mean, most of us are big soccer fans, but in a sense, it's crazy because the thing that you're hoping for, the goals, they hardly occur. So, and there is so much time also spent during a football game where just nothing happens. Like when you look at these the efficient game time that's being played, I think you are at about 58 minutes or so if you take out all the rest. Yet there is this overall fascination why we all love it. But exactly this fact makes it also difficult to predict because goals are so scarce. This is why there have also been people who have actually tried to predict individual actions that might happen in a soccer game, and from there try to predict the goal, which is also an interesting fact. That's why in handball you have so many more goals, you can get better predictions. Now for other sports, yes, with a postdoc we have looked actually at Olympic game data from table tennis. That was a bit. We did not have too much data, but that was really a bit disappointing in the sense that we could barely do better with the data that we had than just making a stupid prediction on which player is better ranked. So there really the ranking was such an influence predictor that we couldn't do much more. But in other sports, so we haven't used this methodology yet for basketball, but I've developed with some students a basketball also prediction model. And what else did we look at? Am I forgetting something? We are indeed going to more sports. We're also going to the different injuries because we are working with partners from the medical side in Luxembourg who bring us different medical data. So that's what we now also start to work on. And tennis not yet, but a lot is being done in tennis, but I'm pretty sure that this methodology could also be used. Tennis, we all know that the psychology is a very important aspect.
There's a question online from Xavier asking about what about sports with no balls or matches? I mean, there's an explanation. Play sports like athletics, cycling, or swimming.
Oh yeah. So for cycling, quite recently in Belgium, actually, a team of researchers has written a paper. I think the title was like, "Who is going to need to be the next Pogacar?" Where they were using machine learning to also predict this? Well, there in these sports you can look at the race results, the placements of the different players, and then try use that as a classification prediction. That's what is being done there. In swimming, it would be a bit. In swimming, you could try to predict the times that they swim. In all these sports, something that is interesting is different from making these predictions, but what is being done in some of these sports is like the ultimate world records that could be taken by means of extreme value theory. This is something that has been more looked at. These pure predictions a bit less. So there's room for going into this.
I think one important aspect is the response variable that you consider. So in football, we model the goals, but you could also directly model win, draw, loss. Then you need categorical models, and you could consider it as a ordinal scale, because from the perspective of the first named team, the best thing is a home win, then comes a draw, and then comes an away team win. And for example, in handball, when you also go for the goals, there's much higher number of goals, like, I don't know, 35 to 40 goals per team approximately. And then, for example, the poisson is not so well-fitting anymore. In football, you have between 0 and 5 goals typically, and from time to time, few outliers. So the intrinsic assumption of the poisson that the mean and the variance coincide, right? The lambda poisson parameter is the mean and the variance at the same time, is not so valid in handball anymore. In handball, you have actually under dispersion, right? So the mean is around 35 goals, but the variance is much less than 35 goals, is much less. So, for example, you could then switch to a negative binomial.
Or that's why we have used this convex Maxwell-Poisson distribution and not the Poisson distribution directly, because indeed you have exactly this problem of under or over dispersion.
And if you model tennis, then you're typically interested in just win or loss, because that's the two outcomes. So you can use any binary, and that's typically Bernoulli assumption for that. And if you model world records in, I don't know, throwing something in the Olympic Games or so, then you have a continuous response, but maybe it's skewed. So maybe you should think about an inverse gamma or whatever. So this is definitely one important aspect for the modeler, like which distribution to choose.
There's another question online by Jean-Louis Furi. Did you treat the group stage in the same way as the KO?
Well, what we did is, so we had our model that was trained up at the beginning, and so there were the group matches. And then we were actually, that was a debate that we had: should we retrain the model based on the group matches or not? We did that. We did not do it for each World Cup. It's always a bit a matter of time and when they are. But yeah, we wanted to. We were using some new information from that phase in order to update, therefore, our predictions. But for the rest, you do it in the same way. Of course, in later stages, you can do 2 types of predictions, or actually 3 types of predictions. You can predict up till minute 90, up till minute 120 possibly, or on top of that, the penalty scoring. And penalties, well, we modeled that by a coin throw, because it's a bit difficult to model this in any different way. So that's what we did also when we made these 100,000 simulations. For later stages, we always simulated it like that.
And it's very important. Sorry.
What we try to do, at least from the team perspective, is looking at the historic penalties of the opponent that we face. So you look at all the individual penalties and build a model based on that per team.
Let's say.
Yeah,
that could make sense.
Like in this project, what we did is actually in the training data, where we had like the preceding 4 or 5 World Cups, all the games, we only look at the 90-minute scores. So in the old training data, we had like in a knockout stage game, we took the result after 90 minutes. And as all the simulation of the new World Cup that we want to predict is based on the Poisson, it's a very nice thing that the lambda of the Poisson is also the goal scoring intensity. So if you simulate 90 minutes and then you still have a draw, you just take lambda divided by 3, because the extra time is just 1/3 of the same length. But if you imagine that it's the same scoring intensity, you can simulate. If the simulation tells you a draw, you simulate again with 1/3 of the lambdas. And then we were just very simple and say, if it's still a draw after 120 minutes, we do a coin flip. because penalty shootout is kind of a thing by itself in a sense. If you the UK team, you would have the model that they are always shitty and so on. And how would you do that? We did not want to touch that.
What you said, of course, I mean, for you at club level, that makes perfect sense to look at this from the opponent perspective. For us, this would have led too far in terms of time to also look at that in detail. That's why we did not do that.
And one other thing, because I think you don't yet know it, because it was part of Hendrik's thesis. Hendrik also investigated this data set again, and he added a very simple variable. It's a dummy variable that just tells you, is it a group or a knockout stage game? And we put that in any game of the training data, so we can learn if there is a general lower or higher level of goal scoring, whether it is a group stage or a knockout stage game. And it turns out that there's a much lower intensity for the knockout stage games because the teams play more shy. And then, of course, you can use this dummy variable when you have learned this effect for the scoring. You can also use it in a prediction, right? When you simulate the group stage, the dummy is 0, and for any knockout stage, you change the value for this knockout effect, and then all the teams have a little less scoring.
You think they play more shy in the knockout? I think it's more of a thing that the level becomes closer when you move towards the knockout.
It's different things. The bad teams, like for example, like Malta, if they would ever qualify for World Cup, or like Saudi Arabia, they are simply typically away. They are gone. So the 8-0 of Germany against Saudi Arabia. Well, there is a 7-1 against Brazil that we are very proud of. But that is a real exception in a half final kind of.
Also, goal difference doesn't matter anymore. Just need one more than the opponent, and in the group stage you maybe want to.
In the group stage, some teams really need a good goal difference, maybe because they could be in the same number of points as the other team, so that this is relevant. And in the knockout stage, you just need to win.
That we also wanted at some point, we're thinking if we should add this as another variable is the saturation effect.
The title holder.
The title holder saturation effect, because 2002 France went out very fast, and this actually confirmed itself with so many title holders. Germany that went out so fast. Italy had gone out in 2010 quite immediately. So there was a repetitive scheme. But France in 2022 broke that, but yeah. There was one more question.
I have a question. Like, you are used the statistical enhanced learning with the classical machine learning techniques, but you can see the root mean square error very significant in random classification, like that random forest or XG boost or cat boost. But once you are coming across with a neural network, there is no change at all. So is there any particular reason? Because in the next stage, if you are going to the deep learning or all this kind of thing, we are using this neural network more. So
yes, so this was indeed something that, to be honest, I find it hard to interpret. Why? In general, neural networks they already take so much into account. They reshuffle all the data that you have. That we were thinking that it might be that there's not such improvement. And indeed, here for the root mean squared error, there was no big improvement. So that's what we were kind of believing could happen. That's why we were happily surprised to see that when neural networks were doing a classification model, that there we had still this very strong improvement. So it seemed that at least for this example, for a classification model, neural network could be improved. For a regression model, they could not be improved. Might again be due to the fact that in the regression model you have more information that you feed in just through the data that you have, because you have the number of goals, and that might be that this is helping the neural network way more than just the outcome. But for the rest, it's not clear.
Is it because of the scarcity of the data, or
could be? I don't yet have an answer on this, but I would imagine. Yes, here you have so much less information. That's why the improvement is stronger. But
and what is the size again of the data set approximately?
Wait, this is the training size.
Okay.
Test size.
Because I don't know. I think the more complex the models get, the more tuning is involved.
Yeah.
And maybe 3,000 observations is simply not enough to fully exploit the potential of a neural network. So we had the same thing. We tried out an XGBoost model on the World Cup data where we just have 500, 600 observations, and it was very similar to the random forest. While in massive data sets, the XGBoost could potentially beat random forest, but is heavily tuning involved. Like in the XGBoost, there's like 5, 6 tuning parameters, and maybe if the data set is too small, it cannot fully exploit the potential. But I don't know. I'm not a neural network expert, so that's why.
Can't say that either. But it's a very good question that we want to dig deeper into.
You get any contact from betting companies?
Yes,
Okay.
of course. But yeah, with betting companies, it's tough. They also like to come to conferences, which makes full sense. I mean, of course, they want to see what is being done. Obviously, they are not the ones who will present their models. That makes also full sense. Yeah, it's interesting, but let's say they made the contacts. We did not really respond back. So
As far as you can tell.
yeah. Okay.
So if there are no further comments and questions, let's thank Christoph again, and thanks all for coming.